Hello, everyone. We are the Aeronautics Senior Design team led by Dr. Shadi Majub. The presenters today are Victor Perez, Lorenzo Quijas, and myself, Robert Rodriguez. This year, the SAE Aero East Advanced Class competition will take place in Lakeland, Florida. The design constraints for designing our plane that were to be maintained are a maximum wingspan of 132 inches, have autonomous colonist delivery aircrafts, a static and a dynamic payload, a 750-watt power limiter, and a maximum weight of 55 pounds. The dynamic payload and the CDAs are to be dropped within the 50-foot radius drop zone at varying altitudes, and during this flight, we must follow the given flight procedure. And finally, a data acquisition system that can record altitude and directional feedback. The project approach that we took was a bottom-up management approach. The team was broken down into component-based sub-teams where each sub-team had a team lead, and these leads would then report any issues or challenges to system integration, who would then report to the project manager. And finally, the project manager would report to the CEO. With this approach, each sub-team was able to give themselves tasks that were to be completed through deadlines, and given the virtual learning environment, we were able to successfully complete all tasks set forth. Below, we see the primary deadline schedule we followed throughout this project. Here's a photo of the senior design team consisting of 25 mechanical engineering students. I will now pass it on to Lorenzo for payload and systems.
Hello, next we will be reviewing our system connectivity tree. So the system connection design process was initiated by planning and designing each connection between components in the subsystems of the aircraft. This process was aided by a system connectivity tree as shown. System connectivity trees were integral to the systematic design of the aircraft because all components needed to be accounted for and designed in a compatible manner. In the system tree shown, each system of the aircraft is dissected into the components that comprise the system and is linked together with specific connection types based on their function. There are four major types of connections, including mechanical connections, wired data connections, wireless connections, and power connections as shown. When designing system connections, this tree was constantly referred to by the systems and integration team and all members from each sub-team. So as shown in the, if we take a look at the figure a little bit more, we see all the major subsystems of the aircraft, such as the fuselage, the wing, the data acquisition system, etc. And it shows how each component comes together individually. Next slide, please. So next we will take a look at our payload configuration. The payload was optimized to maximize the points for the SAE competition. It was necessary to utilize the final flight score and the days of habitability formulas in order to understand and maximize the amount of points that would be achieved per flight. The payload weight plays a vital role in maximizing the points due to weight limitations and space constraints of the aircraft. The maximum payload for the team's configuration consists of 3 CDAs carrying 72 colonists total, and it also includes 14 habitats and 7 water bottles. For this payload configuration with a weight of 17.02 pounds, the maximum points achievable for one flight round, assuming a perfect drop scenario, is approximately 32.74 points per round. This was calculated by utilizing a MATLAB code where the days of habitability and FFS formulas were the governing equations. This resulting combination maintains a competitive edge over other teams while economizing the fuselage volume. As seen in the pictures to the right, here is our dynamic payload, which is dropped with our nerf howlers and the water bottles, and our fuselage. This is the volume that needed to be maximized in order to accommodate our payload. And next, I will pass it along to Victor.
Okay, so now we'll move on to the design of the plane. Early on, research was done by each of the sub-teams to determine the design choices of the plane, with MATLAB being used to perform trait studies to select the optimal design for our objectives. The team had 3 different options for the wing shape and opted for a rectangular shape for ease of manufacturability and cost. Additionally, the team had 3 different options for the tail design and decided on a boom tail, with the main focus being on stability and control of the plane. For the fuselage shape, we opted for a round loft in the front and a square loft on the side due to the payload configuration shape and ease of manufacturability. Lastly, we chose a tailless body design in order to maximize the area and weight and prioritize the amount of colonists inside the CDA. Moving on to the moment and CG calculations performed on the plane, here you can see a representation of the moments acting on the plane for different components. Initially, the CG calculations were done using SolidWorks with the results shown in the table. This showed that the CG lies about quarter length of the wing, being the most stable location for the plane. We then decided to calculate the total moment and weight by hand for each of the components to find the CG of the plane and compare the results. The equations used can be seen in the figure for CG, moment, and moment arm. The results showed similar values of those to SOLIDWORKS with negligible errors. We will now go over the process the team used for the CFD analysis and FEA analysis. We started with researching the different components to fit our design, selecting the best design, modeling the component, running simulations on each component with proper boundary conditions, remodeling, and repeating the process until convergence was met for the analysis. On the right, you can see an example of the CFD boundary conditions that were used for the model to model different components. We had the model centered around a big mesh area that is used to mimic real life where the air is free to flow. The flow comes from the inside the inlet and out from the outlet, as shown inside the figure. Next, we'll go into more detail about the aerodynamic analysis, or CFD, performed on the plane, which was done through ANSYS Fluent. A turbulent model of K omega was applied to represent the turbulent flow, with the convergence criteria of 1 to the -6 being used for all studies for more accurate results. All component values can be seen in the table. Some example plots can be seen in the figures above, including wing lift and drag coefficient ratios, the fuselage skin friction drag, and the CD8 converted to approximately the same value as the hand calculations. The static pressure and velocity magnitude are also shown with the contours of the wing from ANSYS Fluent. In addition, SOLIDWORKS simulation was used for the structural analysis, or FEA, of the plane. All components were tested to their respective scenarios with proper boundary conditions applied to each. Listed on the table is the scenario, the boundary conditions, the material, the failure mode, and if the factor of safety was higher than 1.5 for each of the components. The figure above includes a bending test performed on the wing during cruising to see if the wing would break under the lift loads. The wing was simulated to be fixed to the fuselage with a max lift load being applied from beneath the wing. Mesh refinement was performed on each of the tests until convergence was met, which can be seen on the plot. After analyzing the results, the FOS was seen to be greater than 1.5 for the wing, meeting the criteria. I will now pass it back to Robert.
Our aircraft's avionics features two main circuits, the first of which includes the propulsion system and the flight control system, as seen on the first diagram on the left. During our selection process, we utilize online tools and mathematical models such as eCalc to ensure that our motor and propeller combination gave us sufficient thrust output given the power limitations. We also implemented the Gabriel Staples model and references from the Indian River Control Society to identify crucial stability and control functionality of our aircraft. These tools allowed our team to proceed with control surface design through vehicle sizing, as well as finalizing servo selection with respect to our vehicle's weight, material, and payload configuration. A new addition to our flight control system is a 3-axis gyro stabilization unit, which was integrated into our radio receiver controls. This was useful in preparing our aircraft for varying weather conditions and providing fast control response to different air loads. Once our selections were finalized, all results were experimentally verified during ground testing with the servos and a custom designed 3D printed thrust stand for propulsion. The second circuit features a data acquisition system, the first-person view, and payload release servos. The Arduino-based data acquisition system measures altitude, speed, and payload data, and transmits this information to the ground via an RF link on the ISM band. The flight data is then displayed and stored via an Excel-driven graphical user interface. Additionally, the FPV camera system transmits a live video feed from the aircraft so the payload specialist can guide the pilot towards the target area and allow the aircraft to precisely release the payloads. The final diagram on the right is a standalone system for the colonist delivery aircraft avionics. The gliders are autonomously controlled through a flight controller board, which contains an inertial measurement unit, or IMU, and built-in GPS. The ease of integration of the system, as well as PID tuning capability in the software, were deciding factors in the selection process for the CDAs. With respect to testing and validation, in the top left is a picture of the customized 3D printed thrust stand, which was used to mount our motor and propeller for propulsion testing. The video in the upper right is a stream of our data acquisition system being tested on a flight of stairs as high as 13 feet. Also, a screenshot of our Excel-driven GUI is in the bottom right of the slide. The black text streams real flight data, and the Save Trial buttons hold information on the screen for the duration of the flight when toggled, such as payload data. Since we designed our payload to produce more lift by resembling an airfoil shape, we did some wind tunnel testing using a 3D printed scaled-down version of our fuselage to gather more information on its aerodynamic properties. Here we have a breakdown of each subassembly from the fuselage, wing, tail, and CDA. Ensuring our plane had stable and easy to assemble connections was a primary goal of ours. For our tail connections, we used 2 carbon fiber rods wrapped in non-slip tape that will be held with brackets. Our wing to fuselage connections will be held down by 14 nut bolts and 4 flathead Phillips screws. Illustrated in each photo is a tail boom mount connection, tail to fuselage connection, wing and fuselage connection, and the CDA and wing, where the CDA would mount to the servo release system underneath the wing. Here's a photo showcasing our plane assembly and the CDAs, which consist of balsa wood, fiberglass, and carbon fiber rods. The total budget for this project totaled at $11,634, where it came from sponsors, school funding, and fundraising. The fundraising that the team did was through selling t-shirts and stickers. To build the entire plane cost $4,003.26, comprised of both avionic and structure components. A key component we wanted to make sure while building the plane was to have enough money to purchase safety stock items that will enable us to continue moving forward in the event of a failure of a part. For this, we allotted $4,083.52 to purchase extra building material and avionic parts. We left a miscellaneous budget to account for any tools or hardware needed throughout the project. With the online virtual learning environment, we felt as a team, we would be able to overcome and build a plane we set out to make. This was made possible by adding an extra system integration member to the team to help manage subteams and establish risk analysis methods to reduce issues we may face. An innovation we made to the fuselage was given it a more aerodynamic shape. In doing so, we minimized the parasitic drag while taking advantage of the payload configuration to generate lift. Since we had limited resources to build our plane, we took it upon ourselves to learn Fusion 360 and CNC cut, along with hand cutting all components of our plane and assembling it ourselves. Our tail design differentiates between previous aero teams by having better lateral and longitudinal control, along with better controls due to spiraling slipstring from the propeller. Avionics implemented an all-silver release system due to previous teams having unreliable serverless release systems. And finally, having a single spar wing configuration helped reduce weight and cost without compromising structural integrity. In conclusion to our presentation, here's an overview of our design. Our total takeoff weight is calculated at 43.95 pounds, consisting of 7 water bottles and 14 nerf howlers for our dynamic payload, 5 pounds for our static payload, 3 CDAs consisting of 72 colonists in total, and our total measured wingspan comes in at 124.15 inches. For our recommended future works, we would like more trade studies on our experimental designs. We would also like to consider custom fixtures to hold components in place while wood glue cures. And finally, secure manufacturing resources by being able to outsource or obtain better tools for in-house manufacturing and monocoat the entire plane for flight testing. As stated before, we competed in the SAE Advanced Class competition where we submitted a final design report and presented our plane to a panel of judges. As it stands, however, we currently do not have a result scores yet, which we will hopefully know soon. We also presented in the C Symposium where we placed first in wing aerodynamics presentation, second place in our CDA structures presentation, and second place for our fuselage aerodynamics. Thank you. Any comments or questions?
Cool, nice work, guys. You mentioned doing some hand calcs and bouncing that against SolidWorks analyses, and that the deltas were relatively small. Just curious if you could speak to that a little bit.
Yeah, so for some of the components like the wing and tail, since they had a lot of kind of smaller components that comprise of making the whole entire subassembly, we ended up making actual simplified models that we could actually do hand calculations learned through shrink and material classes to perform those tests, and then import that exact kind of that simplified model into SolidWorks, applying the same boundary conditions that we're kind of expecting from the hand calculations to compare them, to basically validate that the SolidWorks is working with the loads and the boundary conditions that we're applying.
Is there, or have you talked about some potential testing you could do to further anchor things?
Yeah, we're planning to test out all basically the components with actual loads being applied to it to basically validate the SolidWorks after with that. But we haven't had the chance to do that, just with a bit of the limitations that we've been going through with trying to manufacture it and everything. But we're hoping to finish that off so we could actually do the test and validate also the SolidWorks after to make sure that the FEA and everything that we're doing was properly done, and our components aren't just being validated through just software.
Cool.
We have a question from the audience. Actually, it's from Professor Biche. He's asking you to kind of give a more, I would say, clear highlight of the differences between this year's design and what the previous teams or the previous team they had.
Yeah, so I can go to a photo here to better illustrate that. We'll go to the full plane assembly. So something different from last year's design to our design this year is our fuselage shape. It's our payload size is a lot bigger now, so that way during the time of the competition, we're able to carry more payload and release it to gain more points for the competition, as well as have more control over our plane. Last year's team did have a dual boom mount, but they were more spread apart. We felt that implementing as well a dual mount design, but mounting them closer together would allow us to have more control over our plane, as last year had a issue with oscillation in their tail. And then also our servo release system. Last year's team had issues where they had serverless release systems to where their CDAs did not release during the competition. So in order to better enable us to make sure our CDAs and payload gets released, we integrated servo release systems into our design.
I'll ask another question then. So is there? So this is a competition driven project, as far as I can tell, right? So are
Yes.
there limitations in terms of the material? So it's pretty much the same question I'm asking. I asked the other team. So is there any limitation in terms of the materials? So what was the reason? So for the choice of materials that you guys are selecting or using?
Yeah, I
So-
could try to answer.
Oh, yeah,
you
go
want
for
to
it.
go ahead? I was going to say, while we're not limited on some of the materials that we could use, duct tape was a limitation. Just like it's funny that they threw it in there, but we weren't really limited in most of the materials that we could use, but we were limited on the amount of weight that we could have on the plane during takeoff. So our limitation was 55 pounds max. That our plane can't be over 55 when it takes off. So we try to utilize lighter materials. So even though we have a big configuration for the payload and everything else, we were still able to maintain under that weight limit when taking off and adding the payload to maximize our points.
And also taking the amount of budget we had into consideration, we felt doing an all balsa wood plane would enable us to test designs and also let us be able to make our plane ourselves. While we did have issues, with outsourcing some of the cutting, like I said earlier, we took it upon ourselves to do it. So being able to do it ourselves and making it out of balsa wood enabled us to do a design that we knew we could make, and then also put it together and just learn from the challenges of putting a plane together that none of us had encountered before.
I see a question in the chat from Khachatourian. What would be your number one lesson learned that you would pass on to next year's team? For me personally, it would be with manufacturing. With the whole COVID thing that happened, it was really hard to try to find an outsource the plane to be manufactured outside the school. We ended up trying to do it inside the school, but at the time that we were trying to do it, the school closed down. So in turn, the machine shop closed down, so we had to outsource it even more. So instead of trying to find an outsource, which was difficult for us, we ended up getting some tools from ourselves and doing it in-house to cut all the parts out and manufacture the plane. So I think definitely securing a manufacturing place or having the proper tools in lab to be able to do it yourselves if something occurs that you can't have it outsourced.
All right. Well, I'd like to thank the Aerospace Senior Design team for the presentation and everybody for their questions.